Now we can kick off our first seminar this semester, and we're gonna have our guest from NSF, Professor Wang. I'm gonna give her an introduction, and then we can have Professor Wang on the stage. So Dr. Wang is the Warren Owen Duke Energy Professor of Engineering and the Director of the I2R Lab at the Department of Mechanical Engineering at Clemson University. She's also currently a Program Director at NSF, where she's in charge of multiple different programs such as DCSD and FRR. She received her PhD degree in mechanical engineering from WPI and also held a postdoc position in electrical engineering at the University of Rotterdam, which is not far away from here. She became an assistant professor at Clemson in 2012 and was promoted to associate professor in 2018 and then promoted to full professor in 2022. She has won a lot of awards, as a lot of you can imagine, including the NSF Career Award and a few other EAP awards from all those other funding agencies. During this her talk today, she will talk about trust-based human-robot collaboration as well as funding opportunities for from NSF. So with that, let's welcome Professor Wang.
Thank you very much for the nice introduction. It is my pleasure to speak here today. So as Gina has introduced, today my talk will be two parts. First, I will introduce my research in terms of trust-based human-robot interaction, and then I will give an overview about the controls and robotics funding opportunities at NSF. So let me start with the introduction of my research in terms of trust-based human-robot interaction. Okay, so my main research interest lies in the controls, decision-making, and the verification and the learning of human-robot interaction systems, and that have several different areas. So first of area that I focus on shared control between human and robot for mobile robots. We basically want to integrate both the human and the robot initiative into the control of either the drone or ground mobile robot. We have extended it to multi-robot system and also the deep shared reinforcement learning, integrating both human intent uncertainty as well as onboard autonomous robot control. And area two is the collaborative robotics. So we have been working on how to integrate human and robot in collaborative manufacturing tasks, such as assembly, co-manipulation and co-transportation, and pharmaceutical co-robots. Area three, symbolic motion planning for multi-robot systems. So we have been working on how to design task decomposition for multi-robot system to make sure an entire multi-agent system can satisfy high-level linear temporal logic, and then how to integrate humans and the low-level controls in the symbolic motion planning framework. And then more recently, we have extended the symbolic motion planning problem into the off-road bounding overwatch tasks by incorporating the reactive learning and the Bayesian optimization techniques, as well as the considering of robustness of the specification in terms of the signal temporal logic. And then area four, connected and autonomous vehicles. We have been focused on how to design human-centered autonomous driving, haptic-based semi-autonomous driving, as well as imitation learning and adversarial inverse reinforcement learning of an autonomous vehicle when they are driving in the environment surrounded by a lot of human-driven vehicles. And then area six, trust and regret modeling. So that is more in terms of the human feeling and the human decision-making model. So when I first entered the area of human-robot interaction, I was thinking that, okay, as long as I can find some models that describe how human works, I can go ahead and just do my algorithms and design my robots. But it turns out at that time, there was not too many models available. So we have to, at the first place, develop and create a lot of models by ourselves in order to actually do the robotics type of job. So we have been working on how to develop human to robot trust model, as well as how to develop humans regret and rejoice model during the decision making under uncertainty. And also, I'm very proudly to say that I'm dedicated to the STEM education, and I have been involved in several projects regarding developing free and low-cost robotics education materials, including textbooks, online course modules, VR simulations, and animations to lower the barrier for students to learn robotics and controls. And we have recently finished our first open access robotics textbook, and it is currently in press. If you are interested in utilizing free textbooks for your robotics class, do let me know, and I can share these resources with you. Okay, so next, let me introduce a little bit about our research on trust-based human-robot collaborative manufacturing. Let me first talk about trust. So why trust is important? We think that there are two main areas that trust need to be carefully studied when humans work with robots. So first is like collaborative tasks. In this kind of situation, we need to understand the human's acceptance and hence willingness to work together so that human and robot working as a team can have improved performance and balance the human experience. Example applications can be human manufacturing or teleoperation work or education. And then for second scenario, that is more adversarial and unpredictable. That can have a situation like when human wants to actually some risk. So that kind of application can be autonomous driving, robotic surgery, or relief and disaster application where humans put themselves in risks when they choose to work with autonomy. Okay, so next, if we go ahead and look at the timeline of the trust research, it is actually not that new. All the way back to the 90s, people in human factors have started to study what is the human-machine trust, and then what is the organizational trust, basically human-human trust inside the organization, and then trust in e-commerce, treating different say business as an agent and studying their risk and reputation, and then further extension of trust into multiple artificial intelligence agents in the system. And then more recently, people have been starting to think about how to study the trust between human and robot, given the recent advancements made in robots. However, if we look at all these current literature, there is a knowledge gap there, which is if we want to know about how to quantify the behavior of the human so that we can design corresponding robot behavior, there lacks such kind of computational models. So there is where our research starts. Okay, so recently I have just published and invited a paper about different computational human to robot trust models. And then inside this paper, I basically summarized the 5 major categories of computational trust models in the literature. I give a brief introduction about the basics about each types of models, and then discuss what are the pros and cons of all these different models. So in summary, the first type of model is the so-called performance-centric algebraic trust models. So this type of model is basically algebraic equations combining different performance measures. It is good because it is very efficient. You can just make observations about the robot and try to calculate what is humans' trust to robot. But the drawback is because it is a calculation, algebraic calculation based on observational data of the robot. So most of the time, this type of trust calculation is actually trustworthiness calculation, which means they are not the actual subjective human trust. The result becomes most of the time inaccurate, and they always ignore the uncertainty, capacity, and the dynamic nature of the trust itself. And then the second type of the trust model is time series based. Because of this type of time series model, it can be used to capture the dynamic nature of the system, usually in terms of first order linear system. It will also be able to capture the multi-dimensional impact factors related to trust. However, because of the time series nature, usually the model assumes a linear form, which is not necessarily true in practice. And also for different performance measures of robot, they are always lack a uniform framework for different performance models. The third type of the model is the MVP or counting p-bits. So the good thing about this type of model is because of the nature of MVP, this type of model can capture both the dynamic and the probabilistic nature of the trust. It also, because of the MVP structure, it offers us a very systematic framework to capture and describe the relationship between robot and different the human to robot trust and different robot actions and the performance. But the drawback of this type of method is because of its computational requirements, it usually is limited to a set of fine-tuned behaviors. If you have some uncertain behavior or unknown behavior that you haven't learned or seen before, then it is very difficult to incorporate into the MVP model. And then usually the trust is coupled with other states like workload, transparency, or things like that, and hence lacks interpretability regarding correctly what is the trust state. And also because of the computational requirement, most of the time, the state described in MVP is discrete. Then comes to the fourth category regarding the Gaussian-based trust model. The good part about this type of model is because of the probability distribution, you can easily describe the trust in a continuous state. And then it is also dynamic and probabilistic through the updates of the probability distribution. And most of the time, you see the literature, it is easily to incorporate the Gaussian-based trust model into either the PoundDP model or the dynamic Bayesian network DBN type of models. But this model also has its drawback because you really cannot justify if the human's trust feeling follows Gaussian-based or beta distribution or Bayesian methods. And then the last category of the model is the so-called DBM-based trust model. The good thing is, depending on what is the machine learning algorithm that you use, the DBM model can incorporate both discrete and continuous trust state. And it can also capture the dynamic and the probabilistic nature because of the Bayesian setup of the model itself. And because it's utilizing a graph-based correlation method to relate different impacting factor with the trust in a relationship, then it's easy for us to interpret what is the factors that affect the trust and what is the output due to the different latent trust state. But the DBM trust model also has a significant drawback in terms of if you want to have an accurate estimation and prediction of the human's trust, then you need to have a very good knowledge regarding the initial probability distribution of the trust, which might not be the case for some practical applications. Okay, and then if you want to see more detail, please check the paper. Okay, and then next I'm going to introduce in a little bit more detail about the specific trust model that my group has been developing. So the first, we start from the time series human to robot trust model, leveraging some existing qualitative results from the human factors research. So it turns out that human to robot trust is mainly dependent on the three aspects in terms of the human characteristics, robot characteristics, and environment characteristics. So we propose this simple first order system, i.e. the current trust is dependent on the prior trust, the robot performance at the current and prior steps, the human performance at the current and prior steps, and the fourth to represent the error term in our model fitting for the first order system. And then in this particular research, we have been focused on individualizing model and utilizing the auto-regressive moving average method to identify parameter of the time series trust model based on the human subject trust data from our robotic experiment. And then later, we have started to work on the DBN trust model to describe human trust in robot. So how it works is here we have a DBN network, and the trust is basically hidden state follows the encoding property. And the input to this hidden trust model is the, as I mentioned before, is the human performance, robot performance, and environment noises represented by the F function. And then the output of this DBN is the human inputs, which can be, for example, the human's intervention regarding whether we want to change the behavior of the robot. Humans self-report regarding whether they have changed in their trust, or direct trust feedback saying that what is my level of trust to the robot at the current time steps. And then by combining this model, we can basically create a trust belief of the human to robot based on the performance and report, as well as the human input. And then we can formulate an iterative calculation equations to dynamically get the evidence and calculate what is my trust belief. And if we look at this calculation for the iterative equation here, we can show that this belief bar is actually the multiplication of bunch of conditional probabilities that we can model, and we can assume different types of probability distributions based on our understanding of the problem. And then after we perform the robot experiments with human in the loop and collect the data, the problem becomes a machine learning problem. And how do we use the data to learn the parameter of the probability distributions, and then use the learning model to do the prediction and check and validate if these predicted trusts actually match the measurement that I have got directly from the human beings. And then to give an example, say for example, if I want to model the probability of human intervene and change the behavior of the robot, given the human's trust, it can be kind of like modeled by a sigmoid function. And then if I want to model the probability of the transition of the current trust from the prior trust, we can assume that it follows normal distribution where the mean trust value can be modeled by a time series trust models. And you may want to ask me, how can I make all these assumptions about the trust transition probabilities and all these different densities? I think we make a guess and a prediction about what might be possibly the probability distribution. And then based on this hypothesis, we collect the data, learn the model parameters. If what we predicted from the model match what we actually observed from the human data, then we can show that at least what we propose is one good model that can explain what's going on. But there's never a ground truth saying that what we have proposed, either in terms of time series trust model or the DBN trust model, is exactly what humans is. Okay, and then we further extend the DBN trust model to the continuous domain, recently in a human-robot co-manipulation application. So in this particular application, we have modeled the robot performance model as the weighted sum of different performances. And we have first looked at the human-robot agreement performance in terms of when the human and robot are moving an object together, in what extent in terms of both the magnitude and the direction of the force that human will match with the robot. And then second, in terms of collision avoidance of the robot. When human and robot move an object together from point A to point B, during this process, how many collisions the robot is able to avoid, both in terms of the human as well as the surrounding objects. And then last, in terms of the distance to the goal, so this represents the progress that the robot is able to make. And then based on this, we utilize expectation maximization algorithm try to learn the model parameter of the trust belief. So we basically, in order to learn the model parameter for this continuous trust state, we utilize the continuous Bowman-Welch algorithm. However, for this traditional continuous EW algorithm, the multiplication of the forward and backward densities will make the probability either extremely big or extremely small. And then in order to overcome this issue, we have proposed a normalized continuous BM algorithm in the E step in order to learn the expectation. And then in the M step, we basically take the partial derivative of the densities to get the parameter estimation. And once we learn this model, we can utilize the prediction of the state to predict what is the trust state and validate with the data that we have collected. And we have also extend the trust model in terms of BBM trust model for the situation of multi-robot system. And in this paper, it is interdependent multi-robot system. So in this case, it means that the trust to the robot between different robots, all the way from robot 1 to robot alpha, that they are not influence each other. And in this particular case, we can model this trust model basically as an input and output factorial hidden Markovian model. And then we can basically first create the joint distribution of all the robots given the performance measure of the team. And because of the pure nature of this multi-robot system, because they are interdependent, we can put them into the calculation of the initial trust, the transition probability between each of the robots, as well as the emission probability between the robot hidden trust state, and their outputs. And then we assume that all these distributions are constructed by the Boltzmann machine, and similarly using the traditional EM algorithm, the expectation and maximization step to learn the model parameters and provide the prediction. And then as a further step up, now we combine both modeling the trust as a continuous state, as well as considering multi-robot system. And now put it one step further. What if we have multiple robots? They are dependent with each other. So in this case, we are considering a platoon type of multi-robot system, in that the trust state of the robot I is affected by the trust state of its preceding robot I-1. And in this situation, we can have a new set of input to our HMM, which is the prior trust state of agent I, the input of DR, which is basically robot performance, and the output is given by the observation plus some noise. And then we can formulate this general state-based formulation of human to robot trust model of this corroborated multi-robot system, and then utilizing the Bayesian inference and the Markovian chain Monte Carlo simulation to learn the model parameters. And on top of that, compared to the traditional sampling method, we're also utilizing the Bayesian optimization method in an active learning approach to make the learning more cost effective. Okay, so this is a little bit about an overview about our work, the trust field. And then next, collaborative robotics in manufacturing. So
yeah, can I ask a question?
Yeah.
Just about the setup. So the trust is a scalar quantity in this case for each robot, is that right?
yes, correct.
And so generally speaking, higher trust is good, lower trust is bad. But with Gaussian, you can have negative trust as well. Right.
Here, so here we actually can have not just a positive trust, it can be all the way from negative to positive.
Okay,
Yeah,
so
that's
negative
right.
means whatever it tells me, I'm gonna do the opposite, basically.
It just says that it has a lower level of trust,
I see.
not necessarily saying that you are going to do something
I see.
opposite, yeah.
So how you use the trust value, you haven't talked about, right? In terms of like what the human does with it. This is
Yeah.
just how to calibrate trust.
So this is actually utilized in an off-road multi-robot motion task. So by getting what is the trust values of different robots, and then we have a trust-based path planning algorithm. So basically, we want to transfer the robot in a way that they are trust-seeking to maximize trust. Yeah. While satisfying the technological specifications.
Can I ask a question? Maybe I missed this part. Trying to model the trust, different model, approaches to model the trust, right? How much this has been incorporated in a control optimization tasks? And can you shed some light on which trust model is actually most beneficial from optimization?
Yeah, so, for the first part of this talk, I have just introduced the trust models, and then for the second part, about the collaborative robotics, I'm going to introduce some way, that I'm going to incorporate trust with our robot control design. And this is just one example. We have been incorporating the trust in different types of frameworks. It can be incorporating it in a control framework, so that the control will consider trust. Or, yeah, I will get more details.
You would show that from the engineering, with the engineering perspective, not necessarily the manufacturing perspective, right?
What
You can mathematicize maybe solve problems or pull out the problem. You are going to get to like the data there.
So I will first formulate the program mathematically, and then figure out what is the optimization or optimal control of my robot, and then test it and collect the data and perform statistical analysis and show how much the statistic significance our proposed outcome will be compared with pure engineering optimization. Okay, so that's how do we actually incorporate these trust models into our robotics control and engineering cover. So we start from about collaborative assembly in hybrid manufacturing cells. So basically, we considered a human-robot collaborative assembly task, where the human and robot will pick up their respective parts from these different games and put it into a shared space. And human will continue to finish these assembly tasks because we are more dexterous, and the robot can be used to perform more repetitive and dull jobs. And here what we do is actually we first utilizing measurement from motion capturing sensors to estimate what is human motion. And then we have trust models, right? So we incorporate the human motion estimation and the trust measurement into a nonlinear model predictive control formulation. And then try to design a robot velocity control to figure out what will be a good velocity control for humans to travel around these paths, so that they can maximize, for example, an objective function in terms of both physical human-robot interaction factors in terms of velocity, as well as social human-robot interaction factors, such as trust maximization, and then compute these control laws and program the robot system to program the robot. And then after we program the robot utilizing both the physical and the social human-robot interaction aspects, we conduct the robotic experiments with human subjects. And then we do a controlled study with the independent variable as these different robot operation mode can be robot controller designed based on just the optimization of physical human-robot interaction factors. The robot behavior controller based on both the physical and social human-robot interaction factors, and then compare them to study the measures of different dependent variables in terms of both subjective and objective measures. The objective measures can be the velocity that the robot actually travels, how much collision that the robot has avoided, and then what is the average time it takes the robot and the human to finish the task. And then the subjective measures can be actually in reality how much human report that they trust the robot, and what is the human's reported perceived workload. And then we compare all these. It turns out that our proposed hybrid manufacturing cell integrating both physical and social human-robot interaction factors can actually outperform the other robot behavior that's purely considering the engineering optimization problem of only the physical aspects in terms of the overall efficiency of the task. as well as the human experience. Then more recently, we started to look at how to incorporate trust into the human robot collaborative manipulation and collaborative transportation tasks utilizing the variable impedance control framework. So how it works is in this type of scenario, we have a common object that human and robot want to move or manipulate together. And we can have several robot manipulators and also some human manipulators. And in this case, we know that the dynamics of the object is given by this formulation here. And the objective of the overall system can be twofold. First, we want to make sure that when the human and the robot work together, ultimately the motion of the object needs to follow some design path, which means through the collaborative manipulation, human and robot will move an object from one position to another location, follow a certain trajectory. And then second, we want to make sure that the amount of force that human and robot will apply on this object will make sure that they can hold these objects together while we want to minimize the amount of force that human will have. That is ultimately our goal to utilize robots, right? So in order to do that, we can utilize the impedance control framework, which is a natural way to design robots to have a compliance motion. And by designing the different impedance controller, we can have different behavior of the robot. And we can also switch between two extreme of robot behavior, all the way from compliant motion that the robot is fully passive and listen to whatever human commands them to do, into the autonomous motion where the robot will have some autonomy based on their confidence and trust in themselves regarding the performance. And then after this formulation, depends on what is the impedance force we want to choose to achieve whichever type of robot behavior. We can calculate what is the designed amount of force we want to act on the objective level. And then based on the inverse calculation through the graph matrix between the human and robot through the object, we can calculate what is the designed amount of force that we should apply by each robot and the factor in order to realize these two goals. And how does trust come into play? So traditionally, if we want to design impedance control to realize, to match what we estimate about the human impact, we can just have damping term with the error term as well as the human impact information. But now we want to augment it on top of just the physical human robot interaction, and also construct a trust measure. And we want to test how much benefit does this trust configuration into the variable impedance force help us to reach a better goal. And also in terms of the collision avoidance, we have also incorporated the trust model and trust measure into the collision avoidance reporting efforts. And then because what we have calculated so far is in a force control framework, where everything is in terms of how much joint torque that you give to each of the robots. However, in reality, most of the collaborative robots or manufacturing robots, they are velocity controlled. So in order to implement the force input into our velocity control robot, we need to further develop the admittance control framework in order to implement it in our mobile manipulator. And then to further allow more flexibility and autonomy of the robot, if humans trust the robot is more, we have designed the blue space task in a hierarchical way, so that whenever we have a more trusted robot, we allow them to have more capability to perform different tasks. And then combining all these different setups, we have tested different behavior of the robot utilizing these mobile manipulators, combining the raw file with the readback. And the goal is for the human and the robot start from this point and eventually move an object to this goal location while avoiding a static obstacle here as well as a moving obstacle like a human that is going to pass by. And we conducted this experiment and performed another test in terms of the statistical analysis. We have tested different robot behavior as well as both objective and subjective measures of the human and robot team. We have also do a paired t-test between the actually computed trust in our model as well as the subjective surveyed trust that we collected from the human beings. So the conclusion is as follows. First, we have tested different robot behavior that includes a pure compliant behavior, that is pure passive, and then a pure autonomous behavior, and then in between a trust-aware robot behavior. That's another level, and then also just a robot behavior only based on the physical human-robot interaction. And then the conclusion is, it turns out that the trust-aware robot behavior, considering both the physical and the social human-robot interaction factors, it is actually can efficiently finish the task while maintaining a relatively high agreement between the human and robot. And also for the compliant and pure physical human-robot interaction, force-based outcome, as well as trust-aware outcome, they are basically safer to work with than compared with a pure autonomous robot. And in terms of the trust, confidence, and engagement for those subjective measures, as well as the workload, humans perceive the workload, the trust-aware robot also exhibit a higher level of these subjective measures. And also particularly, if we compare the trust-aware robot behavior, which combines both the physical and the social aspect, it actually shows a significantly better score as compared to a robot behavior that is purely designed by the physical human-robot interaction. And in particular, in our case, it's a scheme of robot behavior that is purely based on the estimation of human force during the interaction. And then to further verify that our trust match the observed data from our sampled t-test, we can